Speak louder, it's not listening.
Hey everybody, welcome to another Physics with Dr. T. Today we're going to be looking at magnetic fields. Today I've also invited my daughter Jennifer, who you may remember from previous experiences. And today she's going to just kind of drift along. She just wanted to be on the screen with us, so she wants to see you guys, wants you guys to see her. So here she is. In today's episode we're going to be looking at magnetic fields, and this is going to be the most exploratory lab that you've experienced so far this semester. More What's happening here?
Magnetic fields.
Magnetic fields? What do you mean?
Well, I mean, like, north and south. They go together.
Really?
Yeah.
You're north, I'm south?
No. Oh, you're also north. Ew, go away from me.
Well, anyways, this is the most exploratory lab that you've come across in the course of this lab. So hopefully this is pretty much the most fun lab you'll have. But before we get into the details of that, let's take a look at this week's PreLab activity. In today's PreLab, we're going to be using an old friend that we haven't used in quite some time, Firefox. You can find the download link in the PreLab guide. You can also download it from your mobile app store if you haven't done that before today. And today we're looking for magnetometer. So we tap on that experiment. And we find ourselves here at this page, which is blank, and effectively what you're going to do is start recording. Bring a magnet, something that's maybe got some magnetic characteristic nearby, and see if you can find any evidence that a magnet has been brought near the source. Try other materials just to see if they have any effect as well, just to convince yourself that it is a magnetic field that this is sensing. And then once you've got some data comparing a couple objects, just hit pause. Should be able to also take absolute, just look at the total, zoom it in, and then take a look at the information. You can see the magnetic field given in microteslas. It's a very small magnetic field. And then you see the dip in the magnetic field, a little spike here. This is a very zoomed in on 40 to 65 microteslas. You can pick data, go to points on this and just see how much there's a difference between where you move the magnetic field. And mostly this is just, again, exploratory. And then you can do a screen capture and then transfer this to your submit sheet and prepare that for submission. Your goal is to just kind of explore a little bit of the world around you that may have magnetic properties. And there's some items that are listed in the PreLab worksheet that you can take a look at, including the cushion of a refrigerator door. As it closes, there's actually should be a magnetic seal, so you can take a test there. You can test there. Various items that rotate, they probably do so because there's a magnet involved nearby some coils. So you can turn the fan on and see if there's any change on your meter. You can bring a kitchen magnet nearby. You don't want to use anything really strong, just something that can be picked up by the sensor. And you may want to explore around to try and find where the sensor would be located on your phone. If you're using a space heater in your domicile, consider turning it off, taking your magnet sensor over nearby the wire and through near the heating filament. Don't put it in front of the heating filament, just nearby it. And then turn it on and see if you see any spikes or changes. Try to avoid changing your phone too much during these various tests. Bring the magnet, make the magnet change nearby you. And just see what you get as your result. As mentioned, this lab is intended to be exploratory, not quite as data-driven as your previous labs. This is more exploratory, really getting to the bottom and convincing you about the presence of and the nature of magnetic fields. So explore different power sources, electric sources in your house. And that's pretty much it. Make sure you put the picture into the submit sheet and have that printed and brought to lab. Okay, so the first thing that needs to be addressed is where do magnetic fields come from? And by and large, you're going to find that magnetic fields come from the motion of moving charges or flow of current. So here I have a wire that's drawn, got a current flowing in this way, and there's a magnetic field that comes perpendicular to the surface. This is where you see magnetic fields reveal themselves to be a bit different from the types of fields you've worked with in the past. With electric fields, with gravitational fields, you have a point, so you can have a static point source, and the fields just kind of go outward forever. And with magnetic fields, it doesn't work that way. You have a current that moves a particular direction, and the magnetic field that it generates goes in a circular pathway around that. Along the way of your lab activity, you're going to explore that and confirm that that's actually the case. Generally speaking, there are two types of sources for magnetic fields. One is a bar magnet or a hard magnet, and then the other one is a current loop or current carrying wire of some sort, usually in a loop, sometimes in a straight wire. One of the simplest ways that we can observe a magnetic field's presence is with a compass. A compass is designed to be just a simple magnetized strip of metal that has one side indicated to be the north end of the magnetized metal, balanced on a thin needle so it can wobble and rotate very easily. So you just move that into space, and you can see what happens in the presence of a magnetic field is that it wobbles back into place and then settles along the pathway aligned with the magnetic field. This is the equivalent to magnetic fields of a ball rolling to the bottom of a hill and being at the bottom of the hill. Okay, so how do we represent magnetic fields? Usually with arrows, just like we do with electric fields and even with gravity fields, we use arrows. And so one of the most common ways we think about it is a hard magnet or a bar magnet, in this case with a north and a south, and we have lines that emanate from the north going out, curving back around, and then back to the south. Now, the reason why that is going to be explored in the course of the lab activity. But for bar magnets, this is how we represent them. If we're looking at wires, now this is a side view of the magnetic field, but there's other ways because magnetic fields are, as you will find, perpendicular to the current that's generating them. We need to be able to deal with these in a three-dimensional way. So the most common way to approach this is for magnetic fields that are coming towards you in some kind of a diagram, or coming out of the page, we represent those with dots, as if you're looking at the front end of an arrow. And then if it's the back end of the arrow, like it's going away from you, going into the page, we represent that magnetic field with an X. And so you can see here for a straight wire that the current's going this way. The magnetic field comes out of the board towards you as dots and then re-enters the board as X's, and you'll see it that way. If we, on the other hand, are looking at a straight on to a wire that's coming where the current's coming out of the board, you find that the magnetic field is going around in a circle, around in concentric circles that get further and further apart because they're weakening field as you get further and further away from the current source. And then if the current is going into the board, then the magnetic field curls in the opposite direction. It may have the same magnitude if the current's the same magnitude, but it goes just the exact opposite way. And again, this is a side view of the magnetic field, similar to this guy, whereas this over here is a front or rear view, depending on your point of view, for the magnetic field coming from that same source. One of the more common types of tools that we use for magnetic fields, because of the nature of the relationship between the current and the magnetic field it generates, is what we refer to as the right-hand rule. Today, Jennifer's going to be our hand model for this. And so, first off, before we get directly into that, let's explain what the right-hand rule is. Remember that electric currents are the motion of a positive charge. That's how we've been treating it, even though we know it's negative charges, negative electrons moving. It's a positive charge that we're paying attention to. So the right-hand rule assumes a positive charge in this case. There are three variations of the right-hand rule. They're all consistent. If you pay attention to the details, you should be able to identify that as a confirmed true statement. But for the first one is a loop where the current generates a magnetic field, and you use your hands to do that. So you see here Jennifer will curl her fingers around in the direction of the current flowing around the coil. And you can see her thumb naturally just points upward, and that is the direction of the magnetic field inside the circle that is the area of the coil. Usually when we represent magnetic fields for a coil, it's represented by this expression here. This expression here says the magnetic field intensity at the center of the coil is equivalent to mu naught, that's the permeability of free space, I is the current flowing through the coil, 2r, that's the radial radius of the circle that's carrying the current, and then n, if you have more than one loop, n is whatever the number of coils that are in that loop. And you may run into that, especially in your calculations during this lab. The second configuration for the right-hand rule is reasonably Similar to the first one, in this case, you're going to let your hand follow the field to generate to show which direction the current's flowing. For the second coil, if we know what direction the current's flowing, which Jennifer's going to demonstrate with her thumb going in that direction, then her fingers will then go through the coil in such a way to be consistent with that and wrap around, and that will be, again, indicating the direction of the magnetic field that's generated by the current. Third and final is the Lorentz force. This is the magnetic force acting on a charged particle as it enters an external magnetic field. So here we have the Lorentz force, which is that the force is governed by the electric charge that's moving in the magnetic field, the speed of that charge into the magnetic field, B is the intensity of the external magnetic field, and then sine theta, that's the angle between all the motion and the field that's generated. So for a charged particle, we have our finger pointing in the direction. We have the finger pointing in the direction of the charged particle's motion, and then because the magnetic field that we've drawn is going into the page, I'm going to point this way. Jennifer, on the other hand, her hand is facing, the magnetic field is facing the opposite direction, so she's got to rotate her hand. And now, for my side, it's going to curve upward because my thumb is going to point in the direction of the force, and Jennifer's is going to point the other direction, going in that direction. So that's how you use the Lorentz force for this. All right, good job. That's that. When you first arrive to the lab station, you'll find that your station is indicated as station 0, and there will be a pack with two bar magnets already in place. Also nearby will be a couple of compasses that you can use to map and test your understanding of the magnetic field generated by the bar magnets. I don't want to show too much, but this is the idea. And you'll simply lay the bar magnet on the paper with in the bar that's shown for you and move the compass according to the instructions. The purpose of this is to just get, for the first couple steps of this station, is to get a general idea of how the magnetic field around the bar magnet is, how it's shaped, and whether or not there are complete field lines similar to Earth's, similar to gravity fields, similar to electric fields. No station needs to be done in a particular order. At your first rotating station, you'll go to Station A, magnetic fields, magnetic poles. There's no necessary to go to any particular order. They are just organized for easy designation. But the idea is you've got an oil suspension with iron filings suspended in there, and first thing you'll want to do is tilt it and cause them and re-spread out. Then you'll set this in place and place a bar magnet on it and tilt the magnet. Tilt the page a little bit, let the oils separate in the case. And what you want to pay attention to in this case, more about the gaps between the lines, because the iron filings have started to line up along the magnetic field lines that you should have graphed on, started to see evidence of at your first station, and so you want to sketch those. Try to avoid heavy clustering. We're not paying attention to the iron filings, we're trying to pay attention to the field lines that the iron filings are highlighting for us. So don't focus too heavily on scratching sketches of these clusters of iron filings. Pay attention to the gaps between, and if you need to shake it up a little bit more, let them resettle further into the field lines, then go ahead and make sure that you do that. You want to reset this in between each use, and so you can set the two same side with each other, give it a tilt, and again, take a look at what the magnetic field is doing. Try and sketch the general trends that the iron filings are showing you. Again, we don't want to pay too close attention to the clustering of the iron filings, but to the fields that they are revealing to us. How does that compare to what you sketched with the compass? Almost somebody. All right. What's that? Yes. Once you, your final combination on this is going to be north and south, or opposite sides, and see if there's any reason by looking at the magnetic fields why these attract and the other two repel. For station B, magnetic and non-magnetic materials, the idea is to demonstrate that the magnetic property is not necessarily universal to all metals, but to certain metals. So here we have aluminum, copper, brass, lead ball. This is a nichrome wire, And this has two components to it. The steel band, this is a stainless steel band, and then the screw itself. So you're going to first take a magnetic probe sensor and just kind of, when no magnet is nearby, touch them and see if there's any sign of a magnetic field coming from any of these. There may be. Make sure that they're not nearby each other when you do that, just in case something that is magnetized a little bit is not confusing you accordingly. So you test the magnetic field, and then you bring a bar magnet over close to one, move it away, and then measure it again and see if it's changed any. If it's changed, then it's got acquired magnetic field, and it's a magnetic material. If, on the other hand, you bring a magnet close to something, and then bring the probe over to it, and you can see signs that the magnetic field of that object has changed, then it is a magnetic material. When you get to the station for electric currents from falling magnets, you'll find a coil pack, a magnet that is a strong bar magnet, usually in a package, and you'll want to pop away this, bring this out. And what we're going to do is look at what happens when the current goes near and around this magnetic field. So you begin data collection, and you can just let it run indefinitely. We don't need to get super detailed about this, but what we want to do is see what happens when we move this around, and you can see there is some motion just by moving the magnet around there and moving it back and forth and so forth. Then what you'll want to do is lift this up a little bit of the way, move this inside and see if that makes a difference, and you can see that there is a difference. And then what happens if it moves rapidly through there? Does that make a difference? So you'll move this around just to do a little bit more exploration, and then finally you'll move it and see what happens when it comes to a stop, even though the magnet is inside the coil still. Finally, you'll stop the data collection, restart the data collection, and set it about halfway the height of the magnet. Then drop the magnet north side in first, and then take it out. And then you'll drop it south side first, same height, like so. And then the task will be stop the data, record this sketch on there, and talk about answering the questions that come up. The last station is one that I like to be directly involved with your exploration of. What you'll do is you'll come up to this dipole, this pair of coils, and this will be connected to a 850 controller, and I'll be setting it to about 4 volts. And what you're going to want to do initially before I power it on, move a compass in the vicinity, see if you see any evidence of a magnetic field coming from anything that's on here. So you want to move around the space. The circle that you see in this space is the circle that's printed on your worksheet, and you want to explore the space inside and outside of that to see what direction the magnetic field goes, if there is any. If there's no sign of evidence of an external magnetic field except for the Earth's magnetic field, then we plug in the power to this and we observe whether or not a magnetic field is generated, and the direction that you see a magnetic, if one's generated, you will draw on your paper using the dots and crosses that you're seeing in the theory. You'll also want to explore whether or not, going around in a tight circle, is there evidence of that magnetic field going in a circle around this coil, and whether or not the idea of a north or a south is realistic. Finally, I'll make a demonstration about how this type of magnetic field is used in modern medicine. With the power on, you'll also want to measure the magnetic field right here at the center of the coil, right here about halfway between the center of the coil and the edge of the coil, and halfway between the two coils in the space between. And perhaps the most fun station is a dipole magnet. This is the small one. There's also the large one. And the idea is to use paper clips and kind of explore the magnetic field and see what happens based off of the questions that you see there. Using a nice straightened out clip, you can explore what's happening with this magnetic field as you fling various paper clips around it. You can also map the magnetic field and sketch the idea based off of what this field map shows you. It can be helpful to put a plastic or a paper sheet in order to illuminate how that magnetic field looks at various positions around the magnet dipole. Well, that's all the time that we have for today. If you have any questions, make sure that you ask your TA. You can ask me. This is very exploratory, so it's really about you just playing with the magnets and the different ways of generating a magnetic field. We'd like to thank Jennifer for participating and helping out today. Mostly she just wanted to be on the TV with you guys, so here she is.
This isn't the TV.
I want to thank Jennifer for being joining us today.
Yay.
Say it again. Say magnets are weird again.
Magnets are weird.
And if you have any other questions, until next time, we'll see you in the lab. Lucy wants to also say.
Oh, yeah. Outtakes are awesome too. But magnets are weird.
All right, I'll be like, all right, that's all it is. Make sure I show you. Thanks to St. Jennifer for being a part of helping out today.
All of the outtakes are going to be about me.
And just walk off screen.
That's my school faces east.
The movie The Ten Commandments.
Drink your Diet Pepsi.
Look, it's almost empty.
I'm struggling.
Yeah, you are.
What if you're doing it wrong? What if you're talking wrong?
Again, I created the show. Grab that microphone.
Yeah, but
bring
the
it
show's
in.
not about you.
No, the show's a little bit about me.
Not at all about you.
What is the magnetic field? Oh, it's the car. Nope, that's supposed to be.
Forget your voluntary.
Quiet, you. All right, and that. Right here. Hand me the. So, all right, you ready for this?
I'm gonna go magnets are weird, and then I'm gonna do this, and the screen's gonna freeze, and it's gonna turn gray, and there's gonna be a quote: "Magnets are weird" by Jennifer Tracy. Nuh-uh. Yes, I can win every argument with nuh-uh. That's how it works.
Is that a fact, huh?
This is a fact. So now, go with me. What?
I'll let you watch the outtake of this one.
No.
You tell me if you were a good actor.
I'm a great actor.
Only useful for the outtakes. That's the only thing that she's doing. Well, anyways, this is all the. Wait, hold on. All right, stop laughing out loud. Well, anyways, you talk to me, talk to TA, etc.,
You
etc.
should like move this a little bit over because you're like on the thing.
Yeah, I'm at the center of the thing. I'm the star of the show.
No, you're not.
I wrote the show. This is my
Magnetic
show.
fields are the star of the show. You're nowhere close. You're not made out of metal.
All right.
Star of the show. No, magnetic fields are. Why did north and south go to each other instead of north and south and south and south?
That's a great question because these guys are going to ask that same question and discover. I'm looking at it. All right. We'll come. Okay. All right. No, don't stop telling me what to do. You're off the screen. I have to cut that. Okay. All right. Ready?
It is the
Focus.
thriller.
Yeah. Oh, by the way, I told your mother you have to do Thriller as we get closer to after doing that for performance.
What? There was something. Okay.
All right, you ready for this?
Yeah.
Can we do this? All right, there it goes. Okay,
My hair.
let's take a look at this week's pre-lab activity. Okay, so now
I'm a PreLab activity, guys.
Good grief. You. All right. In today's episode, we're going to be exploring magnetic fields and trying to get a better idea. This is the perhaps most exploratory. You're supposed to be drifting during this part.
Oh my god.
Your lines. You know your lines are, right?
I don't. I forgot.
It's magnetic fields. North and south are together.
Magnetic field.
That'd be funny if you did that. Magnetic fields. I'm going to start with magnetic fields again, okay?
Okay.
In today's episode, we're going to be exploring magnetic fields a little bit more. And, okay, the timing is I'm going to say magnetic fields. I want you to start drifting in, okay? Just like that, okay?
I'm just gonna.
Yeah, just like that. Not that big. Maybe like a couple of nudges and then a big one like that, okay? Then be like, ew.
Yeah.
So much for acting skills. They've been punished over the last several years. Remember back in the good old days when she was telling me I was not acting well?
You're not acting well.
What are you talking
Very
about?
bad at acting.
I'm giving you directions. You're all like, well, what am I supposed to do then?
Well, that's weird.
Okay. Well, then, do you have a better idea? A magnetic field?
I don't know. I'm just gonna like throw myself out here. Magnetic fields.
All right, you ready for this? Fair enough. All right, you ready? All right, you ready? Tell me that you're ready. Can you speak clearly, project, and perform? Are you ready for this?
I'll try.
That's the most I can ask. All right, here we go.
Yeah.